It's just basically a class of problems we're going to learn how to solve. Okay, so welcome back. Using what we have learned, we now have all the tools to solve modeling and optimization problems. Sometimes we call these max-min problems, and there's a basic strategy to approaching them, all right? All modeling and optimization problems is you're given some problem, you frame it mathematically, solve it mathematically, and then you get your answer. All right. So that sounds confusing, but we're going to go through an example of a modeling optimization problem and show you what I mean by that. All right.
Okay.
So here's a question. What two numbers add to 20 and have the largest product possible?
Add to 20 and have the largest product possible.
All right.
10 and 10?
I think that might be the right answer if I'm being honest, but we're gonna show how to do it mathematically. I forget what the answer is, but the idea is we're just trying to frame this mathematically. Let's say our first number is x. Then our second number has to be 20 minus x, right? Because they have to add to 20.
I agree.
Cool. So the product of the two numbers is going to be x times 20 minus x.
Okay.
So let's say this equals product.
Yes.
So the product equals negative x squared plus 20x.
Yeah.
All right. So where do you think the max product is going to? We know this is a function, right? So we're basically looking for the maximum of this function.
Okay, yeah.
Because that's where the product is going to be the largest.
Yeah.
All right. So we can do that by taking the 20x, by the way, taking the derivative of this function and setting it to 0.
Yeah.
All right. Am I going too quickly, or do you get what I'm doing here?
Nope. I'm on board. Yeah.
Okay, cool. Then I'll just do some algebra, and I get that x equals 10.
Yeah.
Right. So then if the first number is 10, the other number has to be 10 as well because they have to add to 20.
20 minus x.
So then we just solved our problem. The two numbers that add to 20 with the largest product are 10 and 10.
Nice.
So do you see how I took a problem, framed it mathematically, solved the problem mathematically, and then I interpreted my answer, right?
Yeah.
What I mean by interpreting my answer is I got x equals 10, and I interpreted that to mean that the first number is 10 and the second number will be 10 as well because they have to add to 20.
Yeah.
Cool. So do you see how these kind of problems are just modeling things with math and then solving those math problems with what we learned in the first half?
Yeah.
And then getting our answer.
Yes.
Cool. Let's do another problem.
Okay.
This one's harder, but I'm going to show you how it's similar. All right. I'm going to draw the first arc of sine of x. All right. Looks like this, right? And I'm going to inscribe a rectangle underneath it. Do you know what that means? All right. And I'm asking, so we're looking at the first arc, which is from 0 to pi, right?
Yep.
This is 0, this is pi. And I'm asking what dimensions of this rectangle will produce the largest area. But it has to be inscribed under the sine curve.
Okay.
All right. So here's what I'm going to do. The halfway point is going to be pi over 2. All right.
Yeah.
I'm gonna do. Here's what I'll do. So I'm gonna label the point from 0 to the start of the rectangle as x. All right. So then the distance from 0 to the start of the rectangle is the same distance from pi to the end of the rectangle because we have symmetry.
Wait, say that one more time?
I said, so if the distance from 0 to the start of the rectangle is x, the distance from pi to the end of the rectangle is x as well because there's symmetry. All right. So that means that this part of the rectangle is pi over 2. That's not pi over 2. Pi over 2 minus x. That's this part of the rectangle. So then the entire base of the rectangle is twice of that. So pi minus 2x. Cool?
Yep.
So this is the base of our rectangle.
Okay.
All right. And the height of our rectangle, if this is an x-coordinate x, then what's the height here? Remember, y equals sine of x. So if this is x-coordinate is x, what's the height of the rectangle here? Because it intersects with the sine function.
Is it y?
It is, but what is y?
Sine x?
Yeah, exactly. Do you see how the height of the rectangle is sine x?
Yeah.
Cool. So the area will be the base times the height. So pi minus 2x times sine x. So I just
Okay.
modeled my problem mathematically.
Cool.
Cool with that? And now I'm asking what x value will make this as large as possible? Because this is the area. I'm trying to make the area as large as possible.
Okay, so then we want to find the first
Yeah.
derivative.
So I'm not this one. The textbook goes through this one. It doesn't do that because it's hard to solve this with algebra because you have sines. So I'm just gonna draw. So you're right. You're good. You're good. But I'm glad that you got that. That's how we would solve it. We would find the first derivative and do the tests. But I'm just gonna do it on Desmos just so we can find the answer graphically because it's hard to do algebra.
Sure.
All right. Okay, so it looks like there's no maximum. But remember, we're only looking at x-coordinates between 0 and pi, right?
Yep.
Because our or actually, take it back, our x value has to be in between 0 and pi over 2.
Yeah.
You agree with that?
Yeah.
So we're just looking for the largest value between 0 and pi over 2. So let me put x equals pi over 2. All right?
Yep.
Largest value occurs here at 0.71.
Okay.
So that's the x value that's going to give us the largest area.
Cool.
So I can write that there.
Plug that in because we have the equation for what it would be if we knew x.
Yep. X equals 0.71. All right. Which means that, remember, the base is pi minus 2 times x.
Yep.
And the height is sine of x. This is kind of curvy. I apologize. So whatever this number is the area of the rectangle. All right. And this is the base, and this is the height.
Word.
So do you see how we just modeled a problem mathematically and used what we know about maximums and minimums to solve the problem?
Uh-huh.
Cool, right?
Yeah, cool.
All right. Awesome. All right. So let me go back here and go to the next slide. Here's the prize problem we just did. How you feeling about those two questions? Because we can do more price examples maybe tomorrow or today, even if you want to. But those are just two examples of what optimization problems look like. It's basically you see a problem, you try and frame it mathematically, and solve the math problem using what we learned today.
Okay, I think I'm good with that.
Cool. Now, we sometimes call these optimization problems because we are trying to find when some condition is optimized, right?
Yep.
We're trying to find when area is optimized, when product is optimized, stuff like that. So that's why we call these optimization problems as well.
Uh-huh.
Right. Examples from economics. Do I care about this? We can just whiz through these because the textbook includes them, and I was tutoring Johnny Kim, and his textbook also included this. So I have no idea if you need to know this or not, but I don't think so. It's just an example from economics.
Yeah.
We'll go through it very quickly. It's not too much.
Okay.
So examples for economics. Some economic terminology. R of X, this function, is the revenue from selling X products. C of X means the cost of producing X products. And P of X is the profit of producing X items, which is your revenue minus your cost.
Yeah.
Cool?
Yep.
In economics, marginal means derivative. So if you see marginal cost, that's just C prime of X.
Okay.
Marginal revenue is R prime of X. All right? So if you're given a revenue function and you're asked to find marginal revenue, you just find the derivative of that function.
Okay.
All right. If we want to maximize profits, we have to find where P of X is at the highest.
Mm-hmm.
So do you see how we just use the rules we talked about from today to figure out where that value is?
Yeah, exactly. Just find the optimal number.
Yep, exactly.
Yeah.
Right, so so if remember, P of X equals R of x minus C of x, right?
Yeah.
So then so then the derivative of P of x equals the derivative of R of x minus the derivative of C of x from our derivative rules. It's just the difference rule.
Okay.
Profit equals cost minus, or revenue minus cost. So the derivative of product equals the derivative of revenue minus the derivative of cost.
Okay.
Does that make sense?
I think so. Yeah.
Okay. So if maximum occur, so if maxima occur when P prime of x equals 0, then 0 equals R prime of x minus C prime of x. Therefore, R prime of x equals C prime of x. That's just a proof for saying that if we want to maximize profits, that will occur when marginal revenue equals marginal cost.
Okay.
We just proved that. Is there anything that I said maximize cost here? I meant maximize profit.
Maximize profit. Yeah.
Cool. Any questions on that?
No, I think that makes sense. That's like a perfect application of it in economics.
Cool. Although these points may be minima, right? Because when the derivative is 0, it could be a minimum point. We at least know where to look to try and find maximum profit.
Yeah.
Similarly to how not all critical points will be maxima, we at least know that the only points that can be maximum are critical points. So we know to look at critical points. Same with here. Although not all these will be maximum, we at least know where to look for them.
Yep.
All right. See how our mathematical tool set allows us to find out how to maximize profit? Look at us go solving real life problems.
Yeah, look at us.
And I say that like half jokingly, but I'm serious. It's really cool. Like it's showing you how calculus really does matter in real life.
Yeah.
Okay. So average cost. Average cost is exactly what it sounds like. On average, what is the cost of producing an item? All right. So it's C of x over x. The reason for that is, remember, if you're trying to find the average of something, you add all the numbers and divide it by the number of things.
Yep.
All right. So if you want to find the average cost of something, you take the cost of all of the things, C of x, and divide it by the number of things, x. So do you see how that's C of x over x is average cost?
Yes.
Cool. If average cost can be minimized, it will occur when its derivative is 0. All right. So it will occur when the derivative of this is 0. If we use the quotient rule, all right, we can find its derivative and set it equal to 0. When we do this, we make a remarkable discovery. The production level where average cost is the smallest will occur when average cost equals marginal cost. And I'm not going to go through the derivation because I just kind of outlined it here, right?
Yeah.
We know it's going to be maximized when the derivative is 0. We find the derivative. We set it equal to 0. We do some algebra, and we get this equation.
Word.
And we interpret what that means. It means, well, then it's going to occur when average cost equals marginal cost.
Cool.
So that's another real-life application in economics.
Nice.
Caution yet again, and then we're done. Note that the previous revelation does not guarantee that there will be a minimum average cost, right? It's the same reason for why a derivative of 0 does not guarantee a minimum there. All right? In neither guarantee, so like for example, we could have a derivative of 0 and there not be a maximum or minima there. So we could have average cost be equal to marginal cost and not have a minimum there for the same reason.
Yeah.
Okay? It neither guarantees that all points where average cost and marginal cost are the same minimizes average cost. It's the same thing. Not all critical points guarantee extrema. So it's the exact same logic.
Yeah.
So not all points where average cost and marginal cost are the same will minimize average cost. Also, there's only one absolute minimum value. So you could have many points where this thing is true, where average cost is marginal cost. But there's only going to be one of them that's the absolute minimum.
Okay.
So just be careful.
Gotcha.
Just like how extrema only occur at critical points, but not all critical points are extrema. We've emphasized that point to death at this point. This does not guarantee that all points with its property will minimize cost for the same reason. All right?
Oh.
It only tells you that wherever average cost is minimized, this property will be satisfied.
Okay.
Any questions on that? I can go through it more slowly and do a different take on it if it's confusing.
I think I get that.
Cool. And also if you're curious on the intuition, it's the same reason for the stuff we outlined before. All right. We said that average cost is going to be minimized when its derivative is 0. We found when its derivative is 0, this is going to be what we get.
Yeah.
All right. But remember, when the derivative is 0, that doesn't guarantee there's going to be a minimum there from all the stuff we talked about earlier. Just because there's a derivative of 0 doesn't mean there's going to be a minimum there.
Yeah.
So just because this is true doesn't mean there's going to be a minimum there either.
Okay. Yep.
That's the logic.
Okay, cool.
Cool with that?
Yeah.
All right. That's all for today. Tomorrow,
right.
we finish Unit 4 with linearization, Newton's method, and related rates problems. And the related rates problem is the BC Calc FRQ 3, maybe? I forget. It's a related rates problem. So we're going to learn how to solve it, and then we're going to do the FRQ on Friday, hopefully. Okay, so what I'm going to do for YouTube is I'm going to end the video. I'll say goodbye, and then Henry, you and I will congregate afterwards. So thanks for watching. I'll see you guys in the next video where we talk about the concepts I outlined here. Have a great day. I'll see you guys later.
Later, YouTube.
Yeah.